Hello friends, welcome to the course Atoms and Molecules for MSc Physics Semester 2 as per the revised syllabus of Savitribai Phule Pune University CBCS 2019 pattern. So we are studying our first module Atoms. So in this lecture, let us study the Hartree Theory. In 1926, Erwin Schrödinger proposed the Schrödinger equations, right? So the Schrödinger equations, they are having two forms. One is time dependent and another one is time independent Schrödinger equation. The Schrödinger's equation is a linear partial differential equation that governs the wave function of a quantum mechanical system. It is a key result in quantum mechanics and its discovery was a significant landmark in the development of the subject. The equation is named after Erwin Schrödinger, who postulated the equation in 1925 and published it is in 1926, forming the basis for the work that resulted in his Nobel Prize in Physics in the year 1933. So, an American physicist, Robert Bruce Lindsay, he was credited for the concept of self-consistency, right? In his study of many electron systems, published in the year 1924, named On the Atomic Models of the Alkali Metals, he introduced the concept of self-consistency in the context of Bohr theory. In 1927, a year after the publication of the Schrödinger equation, Hartree formulated what are now called as the Hartree equations for atom, right? So this Douglas Hartree, he formulated the Hartree theory. So he derived the Hartree equations for the distribution of electrons in an atom and proposed the self-consistent field method for their solutions. Hartree assumed that the nucleus together with the electrons formed a spherical symmetric field. The charge distribution of each electron was the solution of Schrödinger equation for an electron in a potential V of R derived from the field. So self-consistency required that the final field computed from the solutions was self-consistent with the initial field. That means the final field derived from the number of computations that will be similar to the initial field, right? And he called his method as the self-consistent field method. So most of the work in this field has been done by the Douglas Hartree and its collaborators starting in the year 1927 and continuing to this day. It involves solving the time-independent Schrödinger equation for a system of Z electrons moving independently in the atom. So the time-independent Schrödinger equation minus h cross square upon twice m del square psi of xyz plus v of xyz into psi of xyz is equal to e psi of xyz. So in spherical coordinates, we can write this xyz into r theta and phi, right? So we have studied the one electron atoms and multi-electron atoms, right? So compared to the one electron atoms, the multi-electron atoms are quite complicated because they involve more number of electrons, right? And therefore there are more number of interactions there, right? Here we can see the interaction between the nucleus and electron, but here we can see the interaction between the nucleus and each electron and several different interactions between different electrons, right? So this treatment of this many electron atom is quite complicated, but it is possible to treat them in a reasonable way by using a succession of approximations. That means if we apply some approximations, we can treat these many electron atoms, right? So what kind of interactions will be there? So interactions between the electrons and interaction between electrons and nucleus. So we apply different approximations to consider different interactions, right? So we have the Coulomb interaction, that means interaction between electrons and interaction between electrons and nucleus, right? So these important interactions, they are Coulomb interactions, they are taken into account by using first approximation, right? So first approximation, we take into account the Coulomb interaction. And in the successive approximations, we treat the other interactions. So they are less important for us, but we do the calculations by adding these less important interactions in the succeeding approximations, right? That is the treatment we broke into some simple steps, right? In the first approximation, used in treating a multi-electron atom of atomic number Z, we must consider the Coulomb interaction between each of its electrons of charge -e and its nucleus of charge plus Ze. Due to the magnitude of the nuclear charge, this is the strongest single interaction felt by each electron. But even in first approximation, we must also consider the Coulomb interactions between each electron and all the other electrons in the atom. These interactions are individually weaker than the interactions between each electron and the nucleus, but as we can see in the case of helium atom as an example, they are certainly not negligible, right? And furthermore, in a typical multi-electron atom, there are so many interactions between an electron and all the other electrons that their net effect is very strong, except if the electron is quite near the nucleus, right? So another requirement of the method is that the first approximation must not be so complicated that the Schrodinger equation to which it leads is unsolvable. That means the first approximation we are considering the interactions, they should not be so complicated, otherwise the Schrodinger equation becomes unsolvable. In practice, this requirement means that in the first approximation, the atomic electrons must be treated as moving independently so that the motion of one electron does not depend on the motion of the others, right? So in the first approximation, what we are treating two kinds of we are considering two cases, right? So we are considering all the interactions of the electrons, that means electrons and nucleus, and electrons and electron interaction we must take into account. So these interactions, they are called Coulomb interactions, right? We must also take into account that when we consider these interactions in the first approximation, these should not be so complicated, otherwise the Schrodinger equation becomes unsolvable, right? Therefore, we have to put another approximation, that means the electrons must be moving independently, right? So we must treat this, they are moving independently of each other, right? Therefore, the motion of one electron does not depend on the motion of the other electron. Then the time independent Schrodinger equation for the system can be separated into a set of equations, one for each electron, which can be solved without too much difficulty since each involves the coordinates of a single electron only. So this Schrodinger equation we can now separate into a set of equations for each electron, right? So for first electron, this is the Schrodinger equation. For second electron, this Schrodinger equation. For third electron, and so on. For many electrons, we get different Schrodinger equations, right? And therefore, it becomes easier to solve the Schrodinger equation for a particular electron separately. And therefore, since we are considering the coordinates of only single electron, for that case it is much easier to solve the Schrodinger equation for one electron. Therefore, the many electron wave function psi is expressed into many one electron wave functions, right? So this psi is the many electron wave function, total many electron wave function. So this many electron wave function psi, we express it into many one electron wave functions. So psi 1, psi 2, psi 3, and so on. So we have discussed two requirements. So these two requirements are, first we must consider the all the interactions, that means all the Coulomb interactions and all other interactions. And another requirement is that the interactions should not be too complicated. The approximation should not be too complicated, otherwise the Schrodinger equation becomes unsolvable. And therefore we put another requirement is that each electron is moving independently of the other, right? So these two requirements, they are in conflict with each other. A compromise between the requirements is obtained by assuming each electron to move independently in a spherically symmetric net potential V of r, where r is the radial coordinate of the electron with respect to the nucleus. The net potential is the sum of the spherical symmetric attractive Coulomb potential due to the nucleus and a spherically symmetrical repulsive potential which represent the average effect of all the repulsive Coulomb interactions between the typical electron and its Z-1 colligus. That means all other electrons, right? So it can be seen from the figure A that when the electron is very near to the center of the atom, the behavior of the net potential acting on the electron should be essentially like that, the Coulomb potential due to the nuclear charge plus Ze. So the reason is that in this region, the interactions of the electrons with the other electrons tend to cancel each other, right? So when the electron is near to the that of the nucleus or center of the atom, in that case what happens, the interactions due to all other electrons, they will cancel each other, and what we see, a net potential that is experienced by this electron is only due to the nucleus, positively charged nucleus, right? So the nucleus having charge plus Zd, so this positive potential will be experienced by this electron, right? All other repulsive potentials due to all other electrons, they will cancel each other for this case, right? So from figure B, it can be seen that very far from the center, the behavior of the net potential should be essentially like that, the Coulomb potential due to a net charge plus E, which represent the nuclear charge plus Ze shaded by the charge minus of Z-1 of the other electrons, right? So nucleus is shaded by Z-1 electrons for this electron, right? So this electron will see nucleus, but it is shielded by all other electrons, right? And all other electrons are Z-1 electrons, right? For atomic number Z, there are Z-1 colligus for this electron, right? So this electron, when it sees this electron, this nucleus, the nucleus of charge plus Ze is shielded by Z-1 electrons, right? So these Z-1 electrons has charge minus Z-1 E, right? So this electron will feel that the nucleus is shielded by this Z-1 electrons, and therefore, so this plus Ze charge of nucleus minus this minus Z-1 E charge of the other Z-1 electrons, that will give a net charge experienced by the electron, that is plus E, right? So we can see for the electron well inside the atom which is close to the center, that will feel a net potential equal to plus Ze, whereas the electron which is far from the nucleus will experience a net potential equal to plus Ze only. Now if our electron is well inside the atom, right, it is not very close to the nucleus, or it is not very far away from the nucleus, right? So it is seen that there is no way to find the net potential for an atom at intermediate distances from its center. So for this electron, there is no way to find the net potential, right? So the problem is that this obviously depends on the details of the charge distribution of the atomic electrons, and this is not known until solutions have been obtained for the Schrodinger equation that contains the net potential. But it can be taken care of by demanding that the net potential be self-consistent, right? So now if the electron is well inside the atom, that means if it is not very close to the center of the atom, it is not very far away from the center of the atom. For that case, there is no way to calculate the net potential experienced by this electron, right? So the problem is that this net potential will depend on the charge distribution of the atom, right? Charge distribution of the atomic electrons, and this is not possible until we solve the Schrodinger equation, right? Because that contains the net potential V of R, right? But we can start with some potential, and we can say that the net potential is self-consistent, right? So what is meant by self-consistent? That is, if we calculate the electron charge distribution from the correct net potential and then evaluate the net potential from the charge distribution, we demand that the potential with which we end up must be same as the potential with which we started. As we shall see, this condition of self-consistency is enough to determine the correct net potential. Right? So the procedure can be explained into the number of steps. Right? So let us say this flow chart. So we take the initial net potential as V of R, and from this net potential in the next step we calculate the charge distribution of the electrons in the atom. Right? From this calculated charge distribution we again calculate the net potential V prime of R, and we can compare this calculated net potential with the initial net potential. Right? If it is equal to the initial net potential, we can say that our potential that with which we started, that is self-consistent. And if it is not equal to initial potential, then in that case we again calculate the charge distribution from the new potential, and again we repeat all the steps until we get the self-consistent potential. Right? So this is the Hartree theory. So we can see the procedure in terms of the number of steps. Right? So in the first step, a first guess at the form of V of R is obtained by taking V of R is equal to minus ZE square upon 4 pi epsilon 0 R for R tends to 0. That means when the electron is close to the nucleus, in that case we can take this kind of potential. Right? And when the electron is far away from the nucleus, we can take the potential that is minus E square upon 4 pi epsilon 0 R. That means when electron is close to the nucleus, we take the potential of the form minus ZE square upon 4 pi epsilon 0 R, and when it is far away from the nucleus, we take the potential of the form minus E square upon 4 pi epsilon 0 R. And for the intermediate values, we take a reasonable interpolation of this potential. Right? So that means for this case, the net potential experienced by the electron is plus ZE when it is close to the nucleus, and when it is far away from the nucleus, the net potential experienced by the electron is plus E. Right? So in the second step, the time independent Schrodinger equation for a typical electron, that means minus h square upon twice m del square psi of r theta phi plus V of R psi of r theta phi is equal to E psi of r theta phi is solved for the net potential V of R obtained in the previous step. Right? So in the previous step we obtained the V of R, or we guessed the V of R. That means we started with some net potential V of R. In the second step we calculate or we solve the Schrodinger equation for this net potential. Right? However, it is not easy to do this calculation because the radial part of the equation must be solved by numerical integration, since V of R is a complicated function. Right? Next, the eigenfunctions for a typical electron found in this step are psi alpha of r theta phi, psi beta of r theta phi, psi gamma of r theta phi. That these are eigenfunctions for different electrons. They are listed in order of increasing energy to the corresponding eigenvalues E alpha, E beta, E gamma for each electron with symbols alpha, beta and gamma. Right? So this alpha, beta, gamma stands for a complete set of 3 space and 1 spin quantum numbers for the electron. A schematic energy level diagram illustrating the effect of exclusion principle in limiting the population of each quantum state of an atom with 6 electrons is shown here. So in the third step, to obtain the ground state of the atom, the quantum states of its electrons are filled in such a way as to minimize the total energy and yet satisfy the weaker condition of the exclusion principle. That is, the states are filled in order of increasing energy with 1 electron in each state. Right? So we have the Pauli's exclusion principle, which states that we have to fill each energy level with 2 electrons with paired spins. Right? However, we are not considering the stronger case of Pauli exclusion principle. So here we satisfy the weaker condition of the exclusion principle only. That means the states are filled with in order of increasing energy, and each state contain only one electron. That is the weaker condition of exclusion principle, right? Then the eigenfunction for the first electron will be psi alpha of r1 theta 1 phi 1. The eigenfunction for the second electron will be phi b r2 theta 2 phi 2, and so forth through the z eigenfunctions corresponding to the z lowest eigenvalues obtained in the previous step, right? So we get different eigenfunctions corresponding to z electrons, right? Now, so in the fourth step, the electron charge distribution of the atom are then evaluated from the eigenfunctions specified in the previous step, right? So this is done by taking the charge distribution for each electron as the product of its charge minus e times its probability density function. So this probability density function is given by psi star psi. So the justification is that psi star psi determines the probability that the charge would be found in various locations in the atom, right? So the probability density times the charge of the electron will give the charge distribution of the particular electron, right? So for each electron we calculate the charge distribution. So the charge distribution of Z minus 1 representative electrons are added to the nuclear charge distribution, a point charge plus ZE at the origin to determine the total charge distribution of the atom as seen by a typical electron, right? Now, then in the next step, the Gauss law of electrostatic is used to calculate the electric field produced by the total charge distribution obtained in the previous step, right? So from Gauss law of electrostatics we can calculate the electric flux, which is equal to the total charge upon epsilon 0, right? And we can calculate the electric field which is equal to the electric flux per unit area, and therefore the integral of this electric field then evaluated to obtain the more accurate estimate of net potential, right? So we started with some net potential, then we calculated the charge distribution for each electron, and we calculate the total charge distribution of the atom, and from that charge distribution using Gauss law we have calculated the electric flux, and from that we have calculated the electric field, right? Now from this electric field we have calculated the potential, right? So we get more accurate estimate of the potential experienced by the typical electron, right? So this new net potential V of R is found generally differs from the estimate that we have made in the first step, right? So in this next step, if it is appreciably different, the entire procedure is repeated starting at step 2 and using nu of V of R. That means we take this new potential and we again calculate the new charge distribution. From this new charge distribution again we use the Gauss law to calculate the electric field, and from that again we calculate the new potential, next new potential, right? So this next new potential is compared with the potential that we use in the previous step, right? So that two potentials they are compared, and if they are equal we will stop. If they are not equal, we repeat the several cycles from 2 to 3, 3 to 4, 4 to 5, again 2 to 3, 3 to 4, 4 to 5, right? So the V of R obtained at the end of the cycle is essentially the same as that we use in the beginning. At the beginning means to calculate that potential, right? We started with some potential, and from that potential in number of steps we calculated some potential, right? So at the final step we obtain some potential, and that potential is compared with the potential we obtained in the previous step, and these two potential, if they are same, then we can say that our potential is self-consistent, right? Then this V of R is self-consistent net potential, and the eigenfunctions calculated from this potential describes the electrons in the ground state of the multi-electron atom. So we can see this in the flow chart. So we start with some guess potential V of r, this case we made from V of r is equal to minus z e square upon 4 pi epsilon 0 r for electron which is close to the nucleus, and if it is far away from the nucleus, we take net potential as minus e square upon 4 pi epsilon 0 r, right? For intermediate values, we take some combination of these two potentials, and in the next step, we calculate the wave functions for each electron, and from the wave function, we minimize the total energy of the case, right? And from that, we calculate the probability density, and from probability density, we calculate the total charge distribution. The total charge distribution for the atom, that means the nuclear charge plus charge of all the z minus 1 electrons. So this net charge is experienced by the typical electron. It is not the total charge of the atom, but it is the charge experienced by a typical electron, right? Now from this charge we calculate the phi e and v prime of r. That means we calculate the electric flux, then we calculate the electric intensity, and we calculate the potential, right? From in the next step, this potential is compared with the potential with which we have started. If it is not equal, then we take the V of r as the new potential, right? And we again go to the step 2, right? So we calculate again these wave functions, and again we repeat this loop, right? If the new potential we obtain at end of the several cycles is equal to the potential used in the previous step, in that case we say that the potential we have used in the previous step is self-consistent, right? So from that self-consistent net potential, we calculate the wave function psi I, and from this we calculate the total energy of the atom, right? And the process is stopped here. So this is the Hartree theory. So in the Hartree procedure, the weaker condition of the exclusion principle is satisfied by the requirement of steps 3, that only one electrons populate each quantum state, right? So here we are not considering the strong exclusion principle, but we are considering the weaker exclusion principle, right? That means we are considering that each level contains only one electron, and because it makes our calculation more simplified and easy to calculate, right? But the stronger condition is not satisfied, since antisymmetrical total eigenfunctions are not used, right? So the reason is that the antisymmetric eigenfunctions would involve a linear combination of z factorial, right? So there are z factorial terms. That means if the number of electrons are more, there are more number of terms we need to consider or we need to take into account, and therefore calculations become much complicated, right? So which is a extremely large number for all atoms except those with very small z, right? So for larger z, the complications are very much, because the for larger atoms the combinations will be z factorial, right? So the procedure is difficult enough as is, and the use of antisymmetric eigenfunctions would make it very much more difficult again. So already the procedure is difficult. Again, if we consider the antisymmetric eigenfunctions, that will make it much more difficult, right? So what is meant by antisymmetric eigenfunctions? So let's say this is particular eigenfunction that consists of, let's say, two electrons with position coordinates r1 and r2, and if we swap these two electrons, so we get a new wave function. So this, if these two wave functions they are equal, then we can say that our wave function is symmetric. If it is not equal, then we can say that it is antisymmetric. That means particles with integral or half integral spin or bosons, they show the symmetric wave functions, and particles with half integral spins, that means fermions, that means electrons, they are antisymmetric wave functions, right? So we need to consider the antisymmetric wave functions into account, but this makes it a very complicated procedure, right? So the Fock was one of the scientists. He made some calculations using the antisymmetrical total eigenfunctions for a restricted selection of atoms. That means for smaller atoms, he did some calculations with his method and he compared his results with those obtained by Hartree, right? So Hartree used the single electron in each state, and Fock made calculation using antisymmetrical total eigenfunction. That means he put two electrons in each state by using Pauli's principle, and he calculated for the same atom, and he made some conclusions, and he verifies that the use of eigenfunctions which are not of a definite symmetry does not introduce a significant error. That means all the calculations done by Hartree are we can say they are not so accurate, but they are close to the calculation that are made by Fock, right? So, however, in the excited states of the atom, the antisymmetrical total eigenfunctions must be used to give a completely accurate description of a system of electrons, right? So, Fock made some modifications in the Hartree theory, and this theory is called as Hartree-Fock theory. In the next lecture, we will study the results of Hartree theory. Thank you.